Hello everyone and welcome to this lecture. In the last lecture, we saw that a to the power k matrix, where a is the adjacency matrix, right? The adjacency matrix to the power k can give you the number of walks of length k between any two vertices. So suppose if you want to find the number of walks of length k between vertex I and j, all you need to find is what is a to the power ijth entry of a to the power k. But then towards the end of the lecture, I asked, but how exactly to find a to the power k when k is large? Okay, and then I promised you the eigenvalues and eigenvectors can help us. How promising is this commitment? We will see in now this lecture onwards. Okay, and ideally now this is the beginning of the actual use of eigenvectors and eigenvalues for our purpose. Okay, so let us start. Okay, so suppose we have a square matrix of order n cross n. Okay, so let us take a matrix A of order n cross n. Okay, how many eigenvalues it will have? It will have n eigenvalues, right? So lambda 1, suppose these eigenvalues are lambda 1, lambda 2 up to lambda n. And let us take some eigenvectors corresponding to these eigenvalues. So suppose I take this as v1, this as v2 and vn. So these are eigenvalues and these are eigenvectors. Remember, there can be many eigenvectors corresponding to eigenvalue. Okay, so and for simplicity I will taking these eigenvectors as normalized eigenvector. That means for every eigenvector the norm is equal to 1, which essentially means that if you take this transpose vi, this will give you 1. Okay, very simple. Now let us write this in a matrix form. Okay, then the use of these eigenvectors and eigenvalues will be apparent. Okay, so I can write a times, suppose this is eigenvector first, second, after some giving some ordering, right? So this is nothing but, if you see it carefully, by the definition of eigenvalue, this will be nothing but lambda 1 v1, lambda 2 v2 and lambda n vn. Very good. And this I can write as this, right? So I can write just by matrix product v1 v2 up to vn, and then you multiply this with a diagonal matrix where on the diagonal there are nothing but eigenvalues, the corresponding eigenvalues, lambda 1, lambda 2 up to lambda. So this is diagonal matrix. Okay, so I mean this is just a basic definition, so nothing very sophisticated here. So I can, so suppose I write it as v and this as d. Okay, now so that means I can write av equal to vd. Okay, now what I can do next? I can take inverse of this matrix and multiply that inverse on both hand side towards, right? So this will give you av v inverse equal to vd v inverse. Now immediately you will be realizing why I am doing something foolish here. Yes, indeed. Maybe v inverse does not exist. Maybe the vectors those I have chosen, the eigenvector that I have chosen, they may not be linearly independent. In that case, this v will be we will have determinant 0 and the inverse will not exist, right? In that case, I cannot write this. This is not true if v is, or v is not invertible, invertible spelling mistake, invertible. Again my English is very bad here. Invertible. Okay, so now So this is not x and this is cross not okay, cross. Good. Now so for the matrix A, if suppose I can find the eigenvectors v1 v2 v1 vn, sorry, if they all are linearly independent, right, to each other, so basically they form a linear independent set, then I can write this, right, safely. I can write A equal to nothing but v d v inverse. What is the use of this? What is use of this equation for such matrix where you can find eigenvectors which form a linearly independent set? Okay, the use is this. Can you do A square? What it will look like? It will be this, right? V d v inverse, then again v d v inverse. This is giving you what? Since this will give you identity matrix, okay, this is nothing but v d square v inverse. What about a to the power k 3? If you again multiply, this will be v d square v inverse. Again do the same thing, v inverse. This will give you what? This will be identity matrix. So this will give you v d q v inverse. Now I hope the things are visible to what I'm going to write next. So what will be a to the power k? A to the power k will be nothing but v d k v inverse. Okay. So basically the power of matrix can be written by just these terms, right? Now remember, what is d to the power k? D is your diagonal matrix, right? Its power k is nothing but the power on the diagonal entries, nothing else. Okay, very simple. Okay, so there are n numbers, you take powers, right? And then you have to multiply with these two matrices. So essentially you have reduced those many number of multiplications, right, to just only hardly two matrix multiplication, and there are basically on diagonals you have to do the exponent, or the power of the numbers on the diagonal of D, right? Very good. Now there is much simpler than this. Something can be done much simpler than this. Suppose in case this V is very special, this V matrix is very special in the sense that suppose something like this happens. V instead of inverse, suppose this is happening. Then our life will be much more easier, right? In that case, V inverse is nothing but V transpose. We may not even need to calculate the inverse, just transpose will help, right? Okay, but for what kind of matrix this can happen? Remember, V transpose V, when I am saying equal to Y, that means every column of V is what? Is basically these vectors are, or these columns are orthogonal to each other, or not only orthogonal, their norms is also one and they are orthonormal to each other. That means this. So if you pick any two column vector, suppose Vi and Vj, okay, their dot product is 0 and dot product with itself is 1. Okay, so when I is not equal to 0. Okay, so such matrix we call orthonormal matrix or orthogonal. Orthonormal, sometime I will use orthogonal, but for the simplicity I will be taking every time these vectors to be normalized vectors. So it's essentially the meaning is orthonormal. Okay, very good. So, but for what kind of matrix this is possible? What kind of matrix this is possible? Yeah. So basically now let me revise till now what we have done. We have actually chosen vectors v1, v2, vn, which were the eigenvectors corresponding to lambda 1 up to lambda n. Suppose if I can choose these vectors to be orthonormal, okay, then my job was much easier. But can this be always happening? Can for every matrix such eigenvectors is possible? basically a set of n eigenvectors which forms an linearly orthogonal set. Okay, which forms an orthogonal set. Okay, and the amazing thing is, for a symmetric matrix, real symmetric matrix, this is always possible. This is always possible, and in fact, this is if and only if condition. If this is possible in the real case, when the entries are real, then matrix has to be symmetric, and the matrix is symmetric, then you can always find n orthogonal or orthonormal eigenvector. This is one of the most beautiful result in spectral theory or linear algebra. Okay, so let us start. Let me first write that statement, because this statement is very useful for us, because in this course we will be thoroughly using the symmetric matrices. Okay, and many times we will be using this. Okay, so let me first write the statement of this theorem. This theorem is also known as spectral theorem. Okay, so let me write the statement first. Okay, spectral theorem. Before stating the spectral theorem, there is a DIY for you. I kind of made maybe a slight shortcut, but the shortcut is this. Okay, suppose AB equal to I, where A and B both are square matrix, right, of same order, then you have to prove that BA equal to I. Okay, please do not take this as an obvious exercise. Okay, try to prove it. So this is DIY for you. Okay, and that's why when I write V transpose, I immediately write V transpose V. Okay, very good. Now let me move towards the spectral theorem. Let me write the statement first. Let M be a symmetric matrix. A symmetric matrix, okay, of order n. Okay, then you can write M as V D V transpose, or equivalently what you can do this, right? So yeah, V transpose M V, yeah, equal to D, where V is an orthogonal or orthonormal matrix. That means this: V transpose V equal to V transpose V transpose, sorry, one more, V transpose equal to identity orthonormal matrix consisting of eigenvectors which are V1 V2 of M corresponding to the eigenvalues lambda 1, lambda 2 to lambda n, okay, and D is diagonal matrix, so we will denote it by this notation, diag, this basically lambda 1, lambda 2 up to lambda 1. Basically this is a diagonal matrix, and on the diagonals there are lambda 1, lambda 2, lambda 1. So this diag will be that notation for diagonal matrix. Okay, very good. Now, how to prove this beautiful result? Beautiful result. Okay, so let us try to prove it. Okay, and we will prove it using mathematical induction on the size of matrices. Okay, so let us go to the proof. The first base case is very simple, right? When n equal to 1, that means this is 1 cross 1 matrix, right? There is just one entry, right? In that case, you can safely write m, because this is just a number, equal to what? 1 m 1 transpose. Okay, v you consider as 1, okay, and then this you can write. So v is your 1, and m is just 1. Again, m is d, right? There is just one entry, diagonal entry, and one transpose. Very good. Results pass. This base test is passed. Okay. Now assume that statement is true. Assume that the statement is true for any symmetric matrix of order n. Okay, for any symmetric matrix of order n. Okay, now let us take of order n minus 1. Okay, and then we will prove for n. Okay, so that will be much easier. Any symmetric matrix of order n minus 1. Okay, now consider any, let us take now, so this is assumption now inductive. Let us take any matrix which is symmetric, any matrix. Okay, so maybe I will always make some mistakes here. Okay, anyway, any symmetric matrix of order n, right, or n cross n. Okay, very good. So let it be m. Okay, now any symmetric matrix m, let me write of order n. Okay. Okay, so how to prove it? How to use basically use of this and base case, and then maybe some other property. Okay. Now suppose that m is the symmetric matrix of order n. Let us take, I mean, it's one eigenvector. Okay, eigenvector and eigenvalue. So suppose lambda 1 is some, or maybe I will, okay, so this is also correct. Suppose v1 is an eigenvector of it corresponding to eigenvalue lambda 1. Okay, clear, right? Now what I can do is using v1, and I am taking v1 as orthonormal. I mean, sorry, v1 is normalized. Basically, the norm of v1 is equal to 1. Remember, I can always I mean, you can multiply an eigenvector with any constant, it will still be eigenvector. So I am by default taking its normalized version. So okay, so now I will make a very clever use of v1. Okay, using v1 I will make a orthogonal set. Let me first write it, then I will tell you what I am doing. Basically what I will do is I will choose x2, x3 and xn vectors from Rn. So all these xi's are in Rn such that this set is ortho. Basically this is orthogonal set basically. So ortho spelling maybe, sorry, orthonormal set. I can always choose. So basically in Rn there are many orthonormal sets. So I am choosing one, right? But the thing is, the first vector I am by default choosing as an eigenvector corresponding to lambda 1. Okay. So lambda 1, and then what I will do? Remember one thing: since matrix is symmetric, since matrix is symmetric, you will always, suppose if I operate this matrix on some vector xi, remember this xi need not to be eigenvectors. Be careful here. Only v1 is eigenvector. Okay, I am not talking about xi's whether they will be eigenvectors or not. They can be any vectors. Okay, now if you do this, if you take dot product of mxi with v1, what will it give? It will give this. Okay, so let me solve it. Very easy. So xi transpose, if you open this, then this will be m transpose, right? And v1, right? Now since m is symmetric, so this can be written as xi transpose m v1, which is v1, which is nothing but xi transpose lambda 1 v1. But since xi and all these xi's are orthogonal to each other and also with v1, so this will give you nothing but lambda 1 xi transpose v1. This will give you 0. Okay, and we will make use of this neat fact very soon. Okay, now what? And let me call this matrix as Q. Okay, the matrix which consists of these vectors. Suppose that Q is this matrix v1 x2 and up to xn. Okay, so suppose this is matrix. Remember Q into Q transpose, or this will be same as Q transpose. This will become to I because the way we have made this set, right? Very good. Now next thing is what will be this quantity? What will be this quantity? Let me check the theorem again. Yes, very good. What will be this quantity? So Q transpose, if you do this, Q transpose M Q. This will be, so let me write this first. So Q transpose will be looking like what? So Q transpose will be nothing but this, right? So Q is there. So something like, so V1 transpose. So these are rows actually, right? X2 transpose. Yeah, and then xn transpose. Very good. M is my same matrix, so M, and then the same matrix, right? V1 x2 up to xn. Very good. And then I think life looks much clear now. Yeah, okay. So this will be equal to V1 x2 and dot xn. Hopefully I'm not making any mistake. Yeah, now this is mv1 m2 v2. So I can actually directly write this as this. Very good. See, mv1, right? So what will be mv1 is a lambda 1 v1. So this will be lambda 1 v1, and for others this will be nothing but mx2 and mxn. Wow, very good. And then we will be now making use of this fact. Okay, so let's see what will be the first entry of this. The first entry is nothing but, so v1, if you multiply this will be a dot product v1 transpose with v1, then it will be what? This is nothing but lambda 1 because v1 is my normalized vector. What will be the second entry here? So the entry here, what will be this? So v1 is then having dot product with mx2. Now we have just seen that the dot product of v1 with mxi is nothing but 0, so this quantity will be 0. In fact, everything will be here 0. Now I can directly write, or maybe you can verify that this is also 0. These things will also be 0. In fact, so I will be using, so maybe I will just use dot here, so that not getting confused. Yes, everything is 0 here. Okay, now what about other entries? So basically what will be this entry? So this will be entry will be what? mx2 is when multiplying with x2 is when having dot product with mx2, and in this way you can fill the other entry. Suppose this matrix is m cap. Okay, what is size of m cap? The size of m cap is n minus 1 cross n minus 1, right? Is it a symmetric matrix? is M cap a symmetric? Symmetric. The answer is yes, indeed. If you take transpose of it, it will be the same matrix, right? So this matrix has to be symmetric matrix, right? And that's why this chunk will also be symmetric. So M hat is also symmetric matrix, and hence I can use my induction hypothesis. That means for this matrix M cap, there exists basically the orthogonal matrix Q dash, such that if and there exists another matrix also. I will tell you what this look like, such that this matrix is equal to D cap, right? Because I am making use of here the induction hypothesis, and so there exists for M there, or M hat, okay, or cap, I don't know. So there exists Q hat such that and D hat such that Q hat transpose times M times Q is giving me this, right? Very, very simple fact due to my induction hypothesis. Now, how can I make use of this fact to prove that for a matrix of order n cross and a symmetric matrix of n cross n, we will get an orthogonal matrix and diagonal matrix such that the condition hold. Okay, it is not very difficult to see if I can make a orthogonal matrix like this. Remember, this is also an orthogonal matrix. If you take P into P transpose P, it will give you identity matrix, because Q dash, because this Q hat is, or maybe, okay. So this is also identity matrix. Just check it. Very, this is a matrix product. Very, very simple. Now what will you do if I, for this equation, remember this equation was coming out to be, yeah, so let me write this again. So Q transpose MQ was giving you, so Q transpose MQ was giving us this matrix, right? Lambda 1, then all zeros here also, and this was some matrix M hat or M cap. Very bad with terminologies. Okay, now what will happen if I do this operation? Suppose if I do this P transpose, and then here if I do P, what will happen? Okay, if I do this here, if you do, okay, maybe some spaces, I have to create some space. Earlier space was good, I guess. So if I do this P transpose, that means 1 0 0 Q hat transpose times 1 0 0, and then this is Q, right? Q hat, yeah, sorry. What it will give? It will give you nothing but this. Just check it. I'm directly writing lambda 1. So this will be again zeros, okay, and these quantities will get multiplied, and this will be nothing but Q hat transpose M hat and Q hat, okay, and this is nothing but this due to induction hypothesis. Basically, I can write this as lambda 1 0 0 0 0 0 0, and this is nothing but D, and I think we are done. Okay, this D is what? This is diagonal matrix. So basically, so what is, so this operation is giving us our diagonal matrix. So one part is done. Now I need to prove that this matrix, in fact this QP, QP whether this is orthogonal matrix or not, because the theorem says there exists an orthogonal matrix, right? This orthonormal or orthogonal matrix, right? I have to still prove that this matrix is orthogonal. But is it that difficult to prove? If you just do this, Q transpose QP, what it will give? It will give you Q transpose QP, but this is already orthogonal matrix, right? This is already orthogonal matrix since here, okay, since the way we have formed this, right? And then this will be, so I think this will P transpose, this will be equal to P transpose P, and P transpose P is also orthogonal identity matrix. So this is equal to identity matrix. So yes, indeed, we have found a matrix which is orthogonal matrix, such that if you multiply the transpose on the left and this matrix on the right with that symmetric matrix, it is giving you a diagonal matrix, okay? But there is something more here. The more is, these should be the eigenvectors and eigenvalues. The diagonal entries of this D will be eigenvalues, and the orthogonal matrix will consist of the eigenvectors. But it is indeed the truth, right? So, but why this is truth? See, if you see that, so I can write this matrix as what? So M QP, so this matrix is orthogonal matrix. This I can write as what? So if you multiply this matrix, this is nothing but QP times this matrix. So let me call it, yeah, so, I mean, let us write as it is. Okay, nothing but, I mean, just you multiply QP on both sides, then you will get this result, right? Okay. And this is what the eigenvalue eigenvector definition is. So you are multiplying with vectors, right? There are vectors which are orthonormal, and these are same vectors, right? And these are nothing but eigenvalues. So lambda 1, so these will be lambda 2 up to lambda n, right? Lambda, and that's all. Okay, so let me quickly revise or recap what I did. I did this. I have to prove that for a symmetric matrix, right, we can always find n orthogonal eigenvectors. Okay, and this we were proven using mathematical induction when n equal to 1. Basically, the base case is very easy. Then I assume that this is true for any n-1 n-1 cross matrix, and then I very cleverly cook one orthogonal matrix consisting of these vectors. Okay, and then it was boiling down to basically it was actually coming out to be this matrix, and here actually I made use of induction hypothesis M dash. So there exists Q dash and D dash, Q hat and D hat, so that this is true. And then we were indeed finding an orthonormal matrix, that was QP, which was giving you another diagonal matrix, which is again n cross n. In that diagonal all the eigenvalues of M are there. So that's all. And maybe at first glance you will not see why, I mean, maybe it's slightly hard to digest at the first glance, but if you revise it and do some small clever example, it will be very super easy and very beautiful indeed, because now we will make use of this theorem very heavily. Now you can find the matrix power. Suppose a to the power 1000 it is given, so it is nothing but, and the matrix is suppose given symmetric. Adjacency matrix is always symmetric, by the way. So a to the power 1000 is nothing but, you find the eigenvectors of matrix, okay, of that A, and then and then these eigenvalues lambda 1 up to lambda n, you do this 1000, oh sorry, 1000, yeah, 1000, and the same matrix transpose. Okay. Okay, but how easy is to find eigenvectors and eigenvalues? Well, theoretically, because we have to solve this characteristic polynomial, and when any polynomial is of degree, suppose in general, suppose it is of degree more equal to or more than 5, then theoretically it is not possible. It is not possible to find the eigenvalues, right? But there are very good way like QR algorithms which can actually give very efficient these eigenvalues very efficiently to I mean to our practical purpose. With this note, I am stopping this lecture. Thank you very much, and now we will see some more applications of eigenvalues and eigenvectors. Okay, great. See you in the next lecture.